Okay, hello, welcome, Honors Physics. We are now doing Chapter 13, Part 3, Fluids at Rest and in Motion. In principle, we're going to be talking mostly about Pascal's principle, which starts on page 352. Okay, Pascal's principle. Basically, what this is going to have to do with is hydraulic systems like the brakes in your car, systems like you see on all sorts of big earth-moving equipment, construction equipment, etc. Hydraulics. Okay, you must have noticed that the force you apply to the brake pedal in your car is pretty small, especially when you consider the amount of force necessary to actually bring your car to a stop. So clearly, the amount of force you push on the pedal is not the same as the force that's actually being applied to the wheels in your car to bring your car to a rest. What's happening is a hydraulic system. Basically, when you press on the brakes of your car, you're actually engaging a hydraulic system. There's actually a piston at the brake pedal. There's going to be another piston and cylinder at the wheel, and connecting the two is going to be a hose. You'll see more how this works in a few minutes, but I just wanted to plant that seed. At any rate, page 352, Pascal's principle. Pascal's principle states that any change in pressure to a contained fluid is felt everywhere equally. Basically, to say this again, if you have a fluid that is contained and you change the pressure change is felt everywhere in the fluid. In other words, you do not end up with a fluid with really high pressure at the top and really low pressure at the bottom. The fluid contained would have the same pressure everywhere. Okay. What does that look like? Well, that looks like basically the pressure before has to be the same as the pressure after. The pressure before has to be the same as the pressure after. Now, we've played this same kind of logistical game with momentum. We played the same kind of logistical game with energy. Same thing here. What we start with has to be the same afterwards, okay? So, a contained fluid and hydraulic system. Let's draw a better picture here. So, thinking about the hydraulics in your car brakes, you would have two pistons. So let's say two pistons. Let's see what we can do here. We have piston and cylinder number 1 connected via hose to piston and cylinder number 2. This movable piston is in a small cylinder, so we could have some force, say, applied here. So that's you, force 1, that's you pressing on the brake pedal. Inside here is a bunch of hydraulic fluid, and there's a little hose here connecting to the large piston. This little one, I should say, has cross-sectional area A1. Over here we have the large piston. This is the part that might be actually pushing on your tires. Here's all the fluid. Okay, and that will end up pushing up with some force. Force 2. And if you imagine, I apply some force, force 1. I apply some force, force 1. I push down on this piston. That piston is going to move downward. That is going to push all that fluid. It's going to push all that fluid and cause the piston on the left over here to move upwards. Okay? So, what happens to the amount of force? Well, the claim is force 1 should be a really small force. You applied a small force to your brake pedal. Force 2 should be huge. The brakes actually applied a huge force to your tires. So force 2 should be much larger. Let's go have a look at how this works. Well, because this is a contained fluid, Pascal says the pressure there should be the same as the pressure there. Okay, that means pressure is force per area, so the force per area there has to be the same as the force per area over here. Has to be. Okay? So what does that mean for our forces? Well, force 2 would therefore be A2 over A1 times force 1. So it's going to be that number times force 1. In our example, A2 is bigger than A1. Let me scroll back and show you. A2, I forgot to draw that over here. That one is A2. A2 is much bigger than A1. So if A2 is bigger than A1, then F2 is much bigger than F1. We've gained mechanical advantage. The force coming on out of the big piston is much larger than the force being applied to the small piston. This is because of Pascal's principle. Any change in pressure to a contained fluid is felt everywhere equally. So, two different size pistons, I can get two different forces. All right, let's go to a practice problem and see what we can do with this. Practice problem, page 353, page 353. Practice problem 23 I'll do right now. The problem says, dentists' chairs are examples of hydraulic lift systems. If a chair weighs 1,600 newtons and rests on a piston with a cross-sectional area of 1,440 centimeters squared, what force must be applied to the smaller piston, which would have a cross-sectional area of 72 square centimeters to lift the chair? Okay? So there's a lever that the dentist moves with his arm, and that lever pushes on a small piston, 72 square centimeters. As a result of that small piston being connected to a large piston with a fluid contained inside, some sort of hydraulic oil, the large piston of area 1,440 square centimeters will apply a very large force and lift the entire 1,600 Newton chair. By the way, it takes a force of 1,600 newtons to lift a 1,600 Newton chair. Just reminding you how weight works. Okay, let's go see what we can do about solving this problem. Let's move all this out of the way, and we are going to do number 23 on page 353. Okay. We were told that the chair has a weight of 1,600 newtons. So that's going to be force 2, the big one. The area of the piston, of the large piston, the piston for the chair, is 1,440 square centimeters. So that's going to be area 2. Okay. Area 1, the small area, we were told was 72 square centimeters. And we're trying to find what small force does the dentist have to apply to the little lever to actually raise the large 1,600 Newton chair. Okay? So that's what we're trying to figure out. So, scroll some more, and what do we have to do? Pressure 1 equals pressure 2. It's a contained fluid, so Pascal applies. Pressure 1 is force per area. Pressure 2 is force per area. Okay. Scroll some more. Force 1 is going to be area 1 divided by area 2 times force 2. So force 1 is going to be area 1 divided by area 2. All of that times force 2, which was 1,600 newtons. And if we do that, we calculate out force 1 is a meek little 80 newtons. So the dentist needs to apply a meek little 80 Newton force, and if he applies a meek little 80 Newton force, he will be able to lift the entire 1,600 Newton chair. Questions, comments, or concerns, try sending via email. At this point, you guys should be able to do numbers 24 through 26 on that same page. You've also got the homework assignment, so you can start working on the homework assignment. For right now, I'm not going to collect these practice problems, but we might do a quiz or something like that in the future, so definitely practice them. Okay, over and out. Take care.